I am Dr. Rajiv Mishra, IIT Patna. So today's lecture is on time and clock synchronization in the Internet of Things. So the content of this lecture is that we will discuss the fundamentals of clock synchronization and the need in IoT and the different clock synchronization algorithms. To understand how the clocks operate in the IoT devices and how they are synchronized in an accurate and efficient manner is the main objective of this particular lecture. So the content of this lecture is the motivation in the following way. So the Internet of Things devices are wirelessly connected, forming a mesh networks, often need for the mutual clock time synchronization to enable chronological ordering of sensor events, coordination of asynchronous processes across the devices, or network wide coordination of actuators. So this is very much essential. Why? Because you know that the sensors are the devices which are deployed, whether it is a smart city scenario or it is an industrial manufacturing unit. So these sensor networks or these sensors together will form a network, and each particular sensor device is having the timestamp with the event when this particular data is now sent. So therefore there is a need of clock synchronization in order to find out the chronological ordering of the sensor events. The data which sensor sends should have the timestamp. To have the correct timestamp, all the clocks need to be synchronized. To find out the ordering of sensor events, coordination of asynchronous processes across the devices, and network wide coordination. So again I am summarizing the content or the motivation of this lecture is that Internet of Things devices which are often deployed and form a connected wireless network, or you can also say it is a network of IoT devices. Now these IoT devices require to send the data with a timestamp. Therefore the clocks are running in these IoT nodes or the devices, and often to have this correct ordering of the events of the sensor data, they require to have the mutual clock synchronization at all points of time. Now this coordination of asynchronous processes also sometimes requires the clock to be synchronized in these IoT devices, and also the network wide coordination of actuators also sometimes require the clock to be synchronized at the actuators. So this particular need in IoT system, which is a system of clocks running at the IoT devices, needs a clock synchronization in a distributed system of Internet of Things network. So here in this lecture we will discuss also, other than the physical clock synchronization, we will also consider that IoT devices may form a distributed system, and therefore the logical clock synchronization principles also very much essential in the IoT network. So we will consider the logical clock synchronization, and in that context we will talk about the Lampert clocks, vector clocks, and these particular clocks will give a timestamp to capture the causality between the distributed events which is captured by the Internet of Things as the distributed systems. So let us see the need for clock synchronization. So synchronizing the clocks in the Internet of Things devices is important for the applications such as monitoring and real time control. So to understand the concept of the synchronization, you can see an example to make it understand the need of clock synchronization in the Internet of Things scenario as well from our life like examples. So you may want to catch a bus at, let us say, 9:05 am, but your watch is off by 15 minutes. So what if your watch is late by 15 minutes? Then you will miss the bus. What if your watch is fast by 15 minutes? Then you will end up unfairly waiting for a longer time than you intended. Therefore if your clock is not synchronized one of these two events may happen. Either you are too late and you will miss the event, that is to catch the bus, or if let us say your clock is fast, then it will be unfair that that event is waiting for a longer time to get executed. So therefore, time and synchronization are very much essential. As far as the distributed time is concerned, the notion of time is well ordered at each single location, but the relationship between the time at different location is not clear. So therefore, there is a need of time synchronization, which we have seen in the previous slide, the example that it requires for the correctness and it requires for the fairness. So to understand the synchronization in an IoT system, we have to now understand the basic principle of synchronization in a similar environment, which is let us say a cloud based reservation system. So when you say cloud, you mean that lot of servers are now running, and now there is a need for the synchronization in let us say airline reservation system. So server X receives a client request to purchase the last ticket of a flight. Now server X timestamp the purchase during the using its local clock, let us say 6 hours 25 minutes, and locks it and replies OK to the customer. That was the last seat. The server X sends a message to the server Y saying that the flight is full. So Y enters the flight as full and puts its local clock time as 6 hours 20 minutes because his clock is late. So therefore 6:20 it will detect that server Y will detect that the flight is full, whereas server X has its clock is 6:25 when he has booked the ticket. So therefore server Z, when queries server X and server Y's log, it is confused that the client has purchased the ticket at X 6:25 and whereas Y has seen that the flight is full at 6:20 time of the server Y. So therefore this is a problem of clock synchronization. The server Y's clock is slower than the server X's clock, so it will not be able to reason why the seat is incorrectly full showing at Z. So what are the key challenges? Key challenges is that the end host in the internet based systems like cloud and similar system is their Internet of Things, each have its own clock, and unlike CPUs, unlike processor within one server or the workstation which share a system clock, this becomes quite challenging in the distributed environment because all the clocks are running autonomously and they can only communicate through the messages. So the processes in the internet based systems follow an asynchronous model where there is no bounds on the message delays and also there is no bounds on the processing delays, and unlike multiprocessor or a parallel system which follows a synchronous model. So let us understand some definitions and then we will see the basic algorithms for the clock synchronization in the distributed system, where we are considering the IoT also as an asynchronous distributed system, where each IoT device, which is a sensor or an actuator, running its own clock nearby in particular device in the embedded system. So an asynchronous distributed system, let us say, consists of number of processes. So whether it is the system or a process, we can interchangeably be using the same notion which may mean the same thing. So for the sake of simplicity, we will be using the term processes. So each process has a state that is the values of the variables. Each process takes the action to change its state, which may be an instruction or a command action, that is the send or a receive action. So, event is an occurrence of an action. So, each process has a large clock which is an event within the process and can be assigned a time stamp and then ordered linearly. In IoT system, we need to know that the time order of events across the process is also in the same manner. So, let us understand using time space diagram the same concept, that this time and space diagram of a distributed execution. So, here let us say that there are 3 different processes. You can think of 3 different IoT devices running these processes, where there is a event happening within that particular process or an IoT system, that is E1, E2, E3 and so on of a process 1. Similarly, for a process 2 or a second internet device is also occurring various internal events happening at that particular IoT device, that is event 1 at process 2, event 2 at process 2, event 3 at process 2, event 4 at process 2, event 6 at process 2, event 5 at process 2. Similarly, for process 3 is also shown in this particular manner. So, as we have mentioned in the previous slide, that for a process 1, this event 1 is an internal event, whereas for process 1, event 2 is the send of a message, is an action event which will send a message to process 2. So, this event E3 for a process 1 is called internal event, and where the 2 other events which is shown over here in process 1, that is event 2 as a message send event and the message receive event. So, either there are, that means the events are either the internal events happening within the process or within the IoT system, or it is sending a message or it is receiving a message. So, there are 3 different type of events only we are considering to understand this particular time synchronization or a distributed execution for the sake of simplicity. Now, let us see the concept of a clock skew and clock drift. So, each process which is running at some end host has its own clock, let us assume that without loss of generality. Now, when comparing 2 clocks at 2 processes, then the definition of a clock skew says that the relative difference in the clock values of the 2 processes is called a clock skew. For example, if one clock is saying 3 o'clock, the other clock is saying 3:30. So, the difference of these 2 clock values, that is 30 minutes, is called a clock skew. Similarly, you can also understand that the distance between 2 vehicles on the road is called a skew. Now, other concept is called a clock drift. The relative difference in the clock frequencies or the rates of the 2 processes is called the clock drift. Now, you know that there is a quartz crystal running the clock at different rates or the frequencies. So, that difference, that relative difference of the clock frequencies is called a clock drift. So, the example is, you can also see from the real life example, that the difference in the speed of 2 vehicles on the road is called a clock drift. So, the distance between 2 vehicles is called a clock skew, and the difference in the speed of the 2 vehicles is called a clock drift. So, clock skew and clock drift, there are 2 fundamental concepts which we will be using here in the clock synchronization in the distributed system. So, non-zero clock skew means that the clocks are not synchronized. For example, if the clock is giving a time 3 o'clock, at the same instance the other clock is giving 3:30, that is, there is a clock skew of a non-zero value, therefore, these clocks are not synchronized. Non-zero clock drift causes the skew increase eventually. So, for example, if a faster vehicle is ahead, it will drift away. If a faster vehicle is behind, it will catch up and then drift away. So, therefore, non-zero clock drift causes the skew increases eventually. So, these two, non-zero clock skew, non-zero clock drift, requires adjustment, and that is called a clock synchronization. So, let us see what do you mean by the clock inaccuracies. So, clock must not only be the synchronized with each other, but also have to adhere to the physical time, which is termed as the physical clocks. So, physical clocks are synchronized to an accurate real time standard called universal coordinated time. So, universal coordinated time is considered to be the correct time, and all the other clocks required to be synchronized with that time. So, however, due to the clock inaccuracies, a timer or a clock is said to be working within the specification if there is a constant rho is the maximum skew rate specified by the manufacturer. So, with this particular notion and given the universal coordinated time and also given the specification, that is the constant rho, and the maximum skew rate which is specified by the manufacturer. So, you can also understand the behavior of a fast, slow and the perfect clock in this particular example shown in this particular figure. So, on the x axis you have a universal coordinated time UTC shown on the x axis, and the clock time you can see, that is capital C, on the y axis, and for the perfect clock this particular rate, that is dc by dt, should be equal to 1. For a slow clock, this dc by dt should be, if it is less than 1, and for a fast clock dc by dt is greater than 1. So, these are all aspects or the clock inaccuracies. Now, how to synchronize, how often to synchronize the clock. So, the maximum drift rate MDR of a clock, that is MDR is defined to be the relative coordinated universal time UTC, is the correct time at any point of time, and maximum drift rate MDR of any process depends upon the environment. So, the maximum drift rate between two clocks with the similar MDR is 2 times MDR. So, given a maximum acceptable skew m between any two pair of the clocks, they need to synchronize at least once every m divided by 2 times MDR time unit, since the time is equal to the distance by speed. So, having understood these concepts, let us see the external versus internal synchronization methods of clock synchronization. Let us consider a group of processes in this scenario. So, external clock synchronization, where each process Ci's clock is within a bounded D of the well known clock synchronization, let us say S, external to the group. So, the process says Ci's clock, Ci minus S, that is the external clock, if we see the skew, that is the difference, and if it is less than D at all points of time, which is a bound which is acceptable, otherwise this external clock may be connected to the universal coordinated time or an atomic clock. So, this particular type of synchronization with the external clock or a universal coordinated time is called external synchronization. Two algorithms, well known algorithms, is based on the external synchronization. They are called Christian's algorithm and network time protocol, whereas the internal synchronization is the synchronization among the pair of processes in the group of processes, that is called internal synchronization. So, every pair of processes in the group have the clocks within the bound D, that is given two clocks within that particular system, Ci minus Cj is bounded by D at all points of time for all processes I and j. So, this is called the internal synchronization, where in the above example we have seen for the external synchronization that every clock, if you find out the skew with the external clock has to be bounded by d at all points of time, that is called external synchronization. So, internal synchronization algorithms are called Berkeley algorithm and data center time protocol. So, external synchronization, if you have achieved with a bound d, this means that you have already achieved the internal synchronization with 2 times d. So, internal synchronization if you have done, that does not imply the external synchronization is met. So, in fact the entire system may drift away from the external clock s. That means that let us understood the basic fundamentals of external time synchronization. Let us say that all the processes P will synchronize their clock with a time server S, which is a universal time. So, how that is all done, we are going to understand using this particular diagram. So, a process P want to synchronize its clock with the time server S. What it will do? It will ask with the server S through a message what is the time at your clock server. So, the server after receiving this message check the local clock to find the time t, and it will send its time t back by a message, and when the message is received the process P will set its time to t, and this way the process P has synchronized its clock with the external clock. But what is the wrong in this entire process? So, you can see that by the time the message has received at P from S, the time of S has moved on. So, this particular time when P is synchronizing its clock, the time of S has already moved from T to, let us say, some little delta t time. So, it is not same. So, this is inaccurate. Okay. So, inaccuracy here is a function of message delays. So, this particular message delay, that is the time when it takes to reach the message, that is called the message delay or a message latency, is the error here in this particular external synchronization. Now, these latencies are unbounded in asynchronous system, means that when the message will be delivered that is not known in an asynchronous system, the inaccuracy is also unbounded in the asynchronous situation. Let us see the Christian's algorithm, how it does this external synchronization algorithm. So, here the P now measures the round trip time of the message exchange. Round trip time means that when the P has sent a message, it will note down its time, and let us say at time t of the clock S, it receives the message and then it will send the message, let us say at time t2 back, and it has received the message, let us say TP1 TP2. So, TP2 minus TP1 becomes the round trip time, the time when it takes to send to S and S gives back the reply. This is called round trip time. So, let us see that P measures the round trip time of the message exchange. So, measuring the round trip time is by sending several messages and noting down RTT and finding the average of it. This is how the Christian algorithm does. Suppose we know that minimum of P to S latency is, let us say, minimum 1. So, this is S to P latency, P to S latency. Similarly, and the minimum from S to P, this latency, let us say it is minimum 2. So, minimum 1 and minimum 2 latencies, they depends upon the operating system overhead also to buffer the messages, and TCP also time to queue the message and so on. So, the actual time at P when it receives the response is between T plus T is the time here. So, let us understand this. So, the actual time at p when it receives the message, that is the response, is nothing but t plus minimum 2. So, this is minimum 2 range from t plus minimum 2 to t plus, this is time t, t plus RTT t plus RTT minus minimum 1. So, that you can see from this particular figure. So, the Christian algorithm, what it does is that it will set the p its time to the halfway through this particular interval, that is divided by 2. So, the error here is at most RTT minus min 1 min 2 minus min 1 divided by 2, that is half of this particular RTT minus of minimum 1 plus minimum 2. So, this is min 1 and this is min 2. So, RTT is this one. So, RTT minus of min 1 plus min 2, this becomes the error, and this is bounded here in this case in the Christian's algorithm. So, here you can also understand through this particular example the Christian's algorithm error bound. So, the client will send the message, let us say at time t0, and let us say that the message is delivered to the server with a delay of t min after t min time. Then the server will give a time at, that is called server time t, and this particular message by which it is sending the reply will take t minimum delay to reach at time t1. So, therefore, this particular time which is elapsed at the server is to be noted as t1 minus t0 minus 2 of t min, considering that t min and so one way latency is, let us say, t min in this case. So, that particular inaccuracy of a result is t1 minus t0 divided by 2 minus t min, and that is all bounded. So, error bounds, here you can see that they are allowed to increase the clock values. For example, if you know the clock synchronization, how to synchronize the clocks. So, you are only allowed to increase the clock value and you are not allowed to decrease the clock value, because the time never goes back. So, may violate the ordering of events within the same process. If let us say you want to decrease, you are decreasing the clock value. So, you are allowed only to increase, but as far as speed is concerned, you are allowed to increase or decrease the speed. Here in this case, if the error is too high, then you take multiple readings and average them. So, another example of a Christian's algorithm is shown over here that we have already explained. So, let us see the next protocol for external synchronization, that is called network time protocol, NTP. So, NTP is used in the internet for time synchronization among their servers or network devices. So, NTP servers is organized in the form of a tree, and each child is a leaf of a tree, that is shown, and each node synchronizes with its parent in a tree. So, the first server is called the primary server, second level servers are called secondary server and tertiary server, and finally you have the client. So, this NTP servers are organized in a form of a tree. Now, let us see the NTP protocol. Here the child will say, let us start a protocol, send a message, and the parent will receive the message, and parent will reply the message at time ts1, which message will be received at time tr1 by the child, and then child will send another message to at time ts2. So, this message will be replied back by parent at time tr2, and which will be received here by the child 1. So, now you have several time stamps, ts1, tr1, then tr2, ts2, and also ts1 and tr2 is also being sent. You have 4 different time stamps, and using offset you can calculate the difference offset O TR1 minus TR2 plus TS2 minus TS1, and you can calculate the error. Let us say that real offset is O real. So, child is ahead of a parent by O real, parent is ahead by minus O real. Suppose one way latency of a message, one is L1 for L2 is for message 2, no one knows for L2 and L2 and L1. So, there are 2 equations. Now, using these 2 equations you can solve O real. So, O real value comes out to be this particular equation, which is nothing but the offset O, which we have simplified. So, O real minus O will become this particular value, which is bounded by the round trip time. So, if you want to understand again, so you can see here that this is the time stamp when server 1 has sent, this is the time stamp of server 1 TS1 and RT2 TR2, and child has received this message as TR1 and TS2. So, these are the message. Let us see from this equation that what is the offset. So, what you will form is TR1 is equal to TS1 plus L1. So, TR1 is equal to, so the TR1 is equal to, you can see that the time when TS1 has sent plus this delay. So, that is what is being added over here, the same concept which we have seen, L1 plus O real. Similarly, TR2 is also given. So, these equations you will solve here in this case, and this particular equation is now, can see that this error is bounded in network time protocol. Now, you have internal time synchronization protocol called Berkeley's algorithm. Here the master polls each machine periodically, asks each machine for the time. Now, can use the Christian's algorithm to compensate the network's latency. So, Berkeley's algorithm is given by Gusla and Jetty in 1989. So, it starts with the master polls each machine periodically, ask each machine for the time. For that it can use the Christian's algorithm to compensate the network latency. Now, when the results are in compute, which includes the master's time, and here the average cancels out the individual clock's tendency to run fast or slow, send the offset by which each clock needs adjustment to each slave. You can understand the Berkeley's algorithm working through this running example. So, as we have pointed out that Berkeley's is internal synchronization algorithm, internal clock synchronization. Here in this example we are having 1, 2, 3, 4 different clocks running, out of which one is the master, which polls with all others clock values, that is called slaves. So, let us say that clock 2, clock 3, clock 4, they will send their time stamp values or clock values to the master, which is having the clock value 3. So, what it does is it will finds out all other clock values except the clock value coming from 4, which is detected as the anomaly. It will not be considered in averaging. So, excluding the clock value of clock 4, they will compute the fault tolerant average of all other clock values. There are 3 different clock values whose average is being calculated as 305. So, what it will do, it will adjust its clock value accordingly, and now it will calculate the difference. For this is 20 minutes difference, for this is plus 15, and this value also will be sent as the difference, and it will now offset as the difference. So, it will send the offset to each client in this case. Let us see another physical clock synchronization, that is called internal synchronization, which is happening inside the data center. That clock synchronization is called data center time protocol. So, you know that in a data center or in a cloud data center, hundreds and thousands of the nodes, they are sending the message with each other through the network, that is called cloud network. So, these devices are running, let us say the protocol, and let us see that these particular devices also need to be clock synchronized, and therefore data center time protocol is an essential requirement, so that all the nodes or the servers inside the data center are synchronized. We are not going in detail, but we will see that it uses the internal clock synchronization, and it runs in two phases between two peers, that is they are running this stack. We are interested only in the physical layer, because that is the hardware, and that particular message passed its time, exchange its time, and now then it will calculate this particular bound of a precision and accuracy. Now, what we have so far seen is the physical clock synchronization, and there are two types of physical clock synchronization. One is the external synchronization with the universal time clock, and this is the internal synchronization algorithms, which we have seen in the terms of data center time protocol, and here we have seen network time protocol as external synchronization algorithms. In every method we have seen a non-zero error. So, therefore, you know that you just can't get rid of these errors because of the message latency, which are non-zero. So, how can you avoid synchronizing the clocks altogether, yet you are able to use some other method for ordering the events in the distributed system. So, ordering the events in a distributed system without physical clock synchronization is a method which is widely used in various applications. So, let us understand this, and it can be applicable as well in the internet, that is a network scenario, internet, that is IoT network scenario. So, in order to order the events across the processes, so we consider the IoT devices running these processes, trying to synchronize the clock in an approach. So, what if we have assigned the time stamp to the event that were not absolute time? Absolute means not according to the physical clock time. As long as these time stamp obey causality, that would work. For example, if an event A causally happened before another event B, then any time stamp of A should be less than the time stamp of B. So, humans use the causality at all points of time. For example, I enter the house only if I unlock it. So, without knowing the clock values, you know that which event has happened before which other event. Similarly, if you have received a letter only after you send it, so sending of a letter happened before you receive the letter. So, without even having the physical clock, ordering the events is possible using the happened before relation, and that is called causality relation. So, using this concept of causal relation of ordering the events without physical clock, without physical time, is the concept called logical ordering, or this kind of ordering is called a Lampert's clock, and given by a famous scientist which is called Leslie Lampert. So, Leslie Lampert has proposed this particular notion, which is used almost in all distributed system and a cloud computing system, and even in the IoT systems. So, about the Leslie Lampert, he is an American scientist, and this work of time and ordering in a distributed system was a seminal work and is being recognized as 2013 Turing Award. This is the highest award in computer science any scientist can get. So these are some of, this is the paper which has received this particular award. The title of a paper is Time, Clock and Ordering of Events in a Distributed System. Now let us understand this work in more detail to appreciate this work and how that is all done without having the physical clock synchronized, yet you can order the events using the mechanism called Lampert's clock. So define the logical relation, that is called happened before relation, among the pair of events, and which is noted down by that relation happened before relation. So this happened before relation follows three different rules. The first says that on the same process, if there are two events A and B, so if you see the local time of A and the local time of B, so the time of A is always less than B. This means that A has happened before B. So A has happened before B if and only if the time stamp of A is less than time stamp of B, and this time stamp is taken from the local clock. Similarly, when P1 sends the message M to P2, so in that case send of a message has happened before the receive of a message. So even without having clock synchronized, so this event can be send and receive can order the event. These are external event, and these two events you can also form a transitive relation, that if A has happened before B, B has happened before C, then A has happened before C. Now these three relations, they create a partial order relation among all the events in the distributed system, and this particular relation is applicable in all the events happening in the distributed system. Let us take this example. In this example you have three different IoT devices, let us say P1, P2, P3 at different locations. So P1 is generating these events A, B, C, D, E. So A is the internal event, B is send of a message, similarly D is the receipt of a message, E is the send of a message. Similarly P2 also has the events happening. Now you can see that A has happened before B. Why? Because it is a internal events. So that is, similarly B has happened before F and A has happened before F. Why? Because A has happened before B is internal event, B has sent a message, so receipt of a message. So sending of a message happened before the receipt of a message using Lampert's clock rule 2. So if you include this A, B and F, so A has happened before F using transitive relation. So likewise you can order the event in this particular manner. So this is called a Lampert's time stamp. So the goal of Lampert's time stamp is to assign the logical or a Lampert time stamp to each events, and these time stamps you know that obey causality relations using these rules. So each process uses a local counter which is nothing but an integer value. Initial value of the counter is 0. So a process increments its counter when the send or an instruction happens at it. The counter is assigned to the event as the time stamp. So this is called internal event rule, which we have seen in the previous happened before relation, which is also defined here in the Lampert time stamp. Similarly the send of a message event carries its time stamp and receive of a event carries the time stamp, and when the message is received, then the clock can be synchronized using the following rule. So that is nothing but the maximum of local clock and the message time stamp plus 1 is done. Take this example that initially all three values are 0 clock values. So the time stamp of first internal event is TS1 and here TS1 at P3 send of an event. So when this particular message is received at P2, so it will carry the time stamp of P3 as 1. So using that particular rule, the maximum of 0 and 1 is coming from this particular message and 0 is the local clock time. So the message, so maximum of 0 and 1 is 1, so it will be the value as 2. So you can see that from 0 the clock value will be jumped to 2 directly. So that will happen here. So, that is what is shown here in this particular example. You can see another example, that the clock value which is being carried by the send message, that is TS2, which is the clock value of P1, when it received over here, the clock value of P1 is 2 and the local clock is also 2. So, the maximum of 2 and 2 will become 2 plus 1, that is called 3. So, this clock value will become 3. So, all the other clock values are calculated here in this case. So, you can see that this particular logical clock obey the causality relation, and you can order the event here in this case. But this causality is not always applicable on all the events. So, those events which do not obey these relations, then they are called concurrent events here in this case. So, pair of concurrent event does not have the causal path from one event to another event. So, Lampert's timestamp does not guarantee to be ordered or unequal, hence the concurrent event are not causally related events. So, therefore, with this drawback, another timestamp is being proposed in the distributed system, which is called a vector timestamp, and it is used in the cloud databases, which we have discussed as the NoSQL database in the lecture 1. So, this particular database uses the vector timestamp. So, each process uses the vector of integer clock. Suppose there are n processes in a group, so n elements will be there. So, process I maintains a vector vi 1 to n. So, jth element of a vector clock at process I will be of vi of j is ith knowledge of the latest event happened at process j. So, implementing the vector clock. So, here you can see that on an instruction or a send event of a process I, it increments only its ith element of a vector clock, and message when it receives a message. So, each message carries the send events vector timestamp, and both these events are used together to synchronize the clocks. For example, on receiving the message at a process I, so its internal event or its internal clock, that is called vi of I, will be incremented by 1, whereas all other clock values in the vector will be now synchronized using this particular equation, that is vi's knowledge of all other clock values is a maximum of the clock values which is brought into by the process, by the message, say, and its own knowledge, whichever is the maximum, will be taken up except for its own message. So, this is called vector clock, and this we will understand using this particular example. For example, that P1 initially all the clocks are 0 0 0. Why? Because this is the clock value of P1, this is P2, this is P3. So, P1's knowledge of P2 is 0, having its timestamp 0, and here for P3 is 0. Now, if P1 will do its internal event, then this clock value will be incremented by 1 only. Similarly, when P1 will send a message, so send of an event will also increment the clock value. So, it will become 2 0 0, and this value will reach over here. Now, when the value will reach over here, what P2 will do? P2 has these values 0 0 0 initially when it receives a message, and the message is 0 0 1. So, it will synchronize its clock as this particular internal event will become 1 0, and this is being seen as the most recent values, and when the message is received over here, then this particular value will be updated. So, how it will be updated? You can see that this is the receipt of a message. So, internal event will increase, so it will become 2, and what about 0? This particular message is carrying 2 0 0. So, this is incremented to 2, whereas between 0 and 1 and 0 0. So, this 0 and 1 will be more updated value over here. So, that is what you know that vector clock. So, vector clocks follow the causally related. So, if the two events are causally related, if and only if this particular vector condition holds for two events, they are concurrent, then these less than relation does not hold. So, they obey the causality, and if two events are causally related, then you can think of it is happening the other one. So, therefore, let us conclude with this discussion that Internet of Things devices that are wirelessly connected in the mesh often needs the mutual clock time synchronization to enable the chronological ordering of sensor events, coordination of asynchronous processes across the devices, or the network wide coordination of actuators. So, this is very much required, because when the sensor sends the data, it also attaches its time stamp. So, all the sensor locations or the sensor devices running at different locations requires their clock to be synchronized. So, therefore, different time synchronization algorithms we have seen, which is applicable in the Internet of Things as well, and we have seen the two algorithms, Christian's algorithm, Berkeley's algorithm, network time protocol, data center time protocol, and we have also seen that there is a error condition, and therefore, with these error possibilities and synchronization very frequently, and it is taking time in the Internet of Things scenario. So, we have also seen a method of logical clock synchronization in the distributed system. Thank you.